Good afternoon, everyone. My name is Stéphane MOCANU, and I have the pleasure to present you our joint awareness and training cybersecurity program set up between the French Alternative Energy and Atomic Energy Commission and the Computer Science Department in Grenoble. The motivation of our project comes from the observation that in the last decade, and more precisely starting with the Stuxnet attack in 2010, the number of industrial control system attacks and cyber incidents is continuously increasing. Therefore, we decided to set up a hands-on cybersecurity training based on the use of an industrial control system cybersecurity range. We develop a hardware-in-the-loop physical process simulation technology that allow us to build the twin SCADA cyber ranges, WonderX and GIX. Now I will let Pierre-Henri THEVENON present you the technical part and the concept of the cyber range.
Thank you, Stéphane. So the WonderX platform was developed during the 3 previous years by the IRT consortium that brings together industrial and academic partners. WonderX is a hardware-software co-simulation environment that has different goals. This platform is mainly dedicated to raise awareness industrials about cybersecurity issues by presenting different attack scenarios based on real cyber attacks. These scenarios show vulnerabilities in industrial networks or devices, but also problems of isolation between information technology world and operational technology world. Technical and organizational measures to secure industrial control system or solution can also be presented. The platform can also be used to test new attack scenarios or innovative solutions developed during research work. In this platform, we have different elements that represent a section of the Purdue model defining most of the architecture of real industrial environment. The physical process is mainly simulated and its behavior is displayed using a projector by analyzing the status of each variables in a database shared with the simulator. This simulator uses many interface boards to communicate with the control command level. The industrial system has real industrial devices and the SCADA. On the same network, we can find the computer of the technical operator. And so this computer is the target of the attacker in many attack scenarios. As we said before, we have a real industrial system with 3 programmable logic controllers, including one for safety. Industrial devices found in electrical networks are present, such as relay protection and breaker. If you want to control an electrical motor, some motor drivers and controllers are also included. A supervisory unit is connected to the safety PLC to help a technical operator that has access to the electrical cabinet. Few industrial networks are used to connect the different elements. Some are serial, such as Modbus RTU and CANopen. Others are based on TCP, such as Modbus TCP. 2 use cases are fully integrated in the WonderX platform with the functional simulator, control command, and the SCADA. The first one is based on an hydroelectric plant, and the second one is the management of hazardous gases in utility rooms. We have 4 interface boards on this platform that allows us to link industrial devices and the computer integrating the process simulator. As control command devices use mainly 24 volt for digital signal and -10 to 10 volt for analog signals, it is more practical to convert all base signals and use a UDP frame to communicate with the computer. Each interface board has 32 digital input-outputs and 16 analog input-output and 1 Ethernet interface. 2 other different boards allow us to use the analog output of the first interface board to generate real electrical signals. Suitable with the use of protection relay, it can be used to generate the free phase of the electrical signals and to stimulate electrical problems, for example, an overcurrent. My colleague Maxime is going to present you the simulator and complete dedicated attack scenarios developed for this platform.
Thank you, Pierre-Henri. The physical process simulator is developed in Python and revolves around the SymPy module, which is a process-based discrete event simulation framework. This allows us to represent each of the components of the simulated industrial process, for instance, a valve or a heat sensor. All objects are scheduled around command clock, and their inputs and outputs are linked accordingly to the scenario. For instance, the output of a gas bottle may become the input of a valve. Then, the simulator both communicates with the interface board presented earlier through a UDP protocol, and also with a graphical representation via a database. We developed 3 scenarios. One simulates white rooms and implies hazardous gas management. Another one represents a hydroelectrical power plant. And finally, the last one is the classical process of Tennessee Eastman, a chemical factory. Hundreds of videos are merged to create a graphical display of each of the physical processes, and XML rules are used to select each video according to the values of variables that represent the state of the simulation. In the platform, 3 screens are managed concurrently. One for the SCADA, one for the graphical representation, and the last one for a slide set with explanations. In order to perform attacks, we developed a whole network of virtual machines embedded in 2 separate networks. This allows us to run destructive attacks and easily reset the platform by simply resetting the VMs to a previous state. First is the attacker network on the left. It includes a VM based on Kali Linux, alongside with a web server that the attacker can use to drop off some payload. On the right is the internal company network, which includes a Windows 7 VM representing the computer of an operator, alongside the company email server, which may be used for phishing attacks. We developed 2 complete cyber attacks. One involves a malicious USB key with a fake keyboard, and the other one relies on a spear phishing email with a malicious Office document starting a remote access Trojan. Both attacks start with a reconnaissance phase that either includes host and port scanning or open source intelligence. Then is the delivery phase according to the attack, and at this point both attack rejoin paths and give access to various charges, going from a cryptolocker to injection of industrial network frames. In this case, these frames are carefully chosen and timed in order to impact the physical process. I will now let Stéphane MOCANU present the DSYS platform that is developed for teaching.
Thank you, Maxime. DSYS is a freely configurable lab built in a Fab Lab spirit. We have more than 100 industrial devices that may be interconnected in a custom system architecture. That will include, of course, PLC, human-machine interface, and the remote terminal unit, but also OPC servers and some 62950 devices. We can build redundant network architecture like HSL and PRP, and we have several precision time protocol sources available. We can interface those materials with practically any simulator software like MATLAB Simulink or Modelica, but also with some commercial training software like Home.io and Factory.io, and of course we can interface it with some custom simulation software. DSYS may be used for training in automation and SCADA system, also in real-time network study, and on the cybersecurity side, we can do vulnerability search studies, pen testing, and reverse engineering. Well, I'll finish with a capture of the system running. You can see in the screen capture the process simulator, a simple SCADA interface, and the development environment of the PLC connected to the PLC, and we can follow the program evolution. Finally, a Wireshark capture can let the students relate the Modbus traffic or the industrial traffic with the actions in the SCADA and the program of the PLC. Well, the whole system, including the electronic car schematics, are freely available and they are downloadable for one of the two addresses in this slide.